Okay, thank you for your presentation. I have three questions. So the first one, have you tried to measure the current of the Pico EMP?
No, actually, that's something I haven't done yet. So
Okay.
yeah.
So the second question is related to, have you tried to inject multiple pulses? I mean, with very short interval between them?
Not with it. So the Pico MP, the one trade-off it makes is it has a pretty small capacitor, like 0.47 microfarads as the storage. It theoretically could work, but the transformer coupling for the gate drive is also kind of slow. So you couldn't do like the 100 nanosecond or something. I think would be too fast. I haven't tried to see how low you could push it. But yeah, it's one of the trade-offs of the design is it doesn't work as well for that. Like it, targets kind of low cost.
Okay.
I think it says safety first, low cost second, and then performance. So
when you compare between the EM and BBI, you see the same effect on the same physical location? I mean, the same physical location that you obtain faults using EM, is it the same when you do BBI?
So on this case, the probe itself, it was a larger, there was a few millimeter probe size. So it wasn't accurate enough that it was able to do that. It's roughly the same location visually, but I didn't make a map with Pico EMP versus BBI. So no, in this case, I can't say for sure, visually roughly, but I wouldn't put that as a reference.
Okay, thank you.
I have a somewhat generic type of question. What are the benefits of EM fault injection over the more classical fault injection types? And if there are any drawbacks?
Yeah, so I think the biggest advantage that I know of is the ease of applying it. So with EMFI, typically we only, have to take the device, put it on the table, and then have the EM probe over it. You don't, like with voltage fault injection, at minimum, you're attaching to the board. Often you end up having to do some power supply surgery, right? With laser, there'd be some decapping, maybe if it's a wafer level through the die, you can avoid it. But it's, the main advantage of EMFI has been that it's really easy to just put the board down, I think in some of those photos, I just have like a vice, right, holding the EM tool. So it's a more practical, when you talk about making a low cost tool, it's reasonable because, I can make a $50 tool and actually say that's all you need. You don't have to have, a positioning table to use it. So the main advantage I see is in the, target preparation work is a lot lower than with most other devices. Or
how about the probability of a successful fault injection experiment?
So it varies on a lot of devices. I see it as quite successful. You have the advantage of you have spatial positioning, right? So with voltage fault injection, you're more limited to get a good success rate, right? All you have to adjust is the parameters of the voltage fault. So if you do the kind of more complex arbitrary waveform generator that we saw before, that's actually a good example of what you might need to do to get really high success rates with EMFI. You also have the spatial, so that tends to be if you find a good spot, right, then the actual glitch parameters are pretty simple. Like it's just maybe voltage and width and time and stuff like that. So that's the other advantage. You have more to play with, right? The disadvantage compared to say voltage fault injection is that, the disadvantage, you also have the spatial. So if I have my EMFI set up and, I think people have surely seen this, you move one thing and it's like, now it's ruined. And now I have to spend a while searching to find that good spot again because I had to, take the chip out because I broke the chip because the EMFI can blow up stuff occasionally. Right. With voltage fault injection, if I solder the wires to the chip in the same spot, it should be pretty reliable. And if someone else does it, it tends to be very, maybe there's some variation, but it's a lot smaller. And with EMFI seems to be.
Okay. Yep. Just a very easy, quick question. Low cost, what does it mean? $50? Was it right?
Yeah, so it's about $50 cheaper if you buy all the parts and build it yourself.
Where can I buy it?
We had some quasi kits. It's not CE certified, so you can't buy it from us officially. But yeah, New AE sold some kind of pre-assembled boards and
okay.
that price range. So.
Are there further questions?
Yeah, so thank you for the talk, and actually thank you for the tools I used already in classrooms and assembled it. And actually on one issue, maybe it comes from the current situation of the COVID pandemic, but the IGBT is hard to get actually in Europe. So the question is, are there any, let's say, how you designed the circuit? Did you design everything around one GPT for driving it, or did you first design the circuit and said, okay, that is what could fit in? Because we're thinking about how to replace this, because this one circuitry was really hard to get 1 year ago.
Yeah, so it's not very sensitive. I mean, the design process was pretty much, we'll use some IGBT. At the time it was available when we did the first run. There's actually been a second part number that's used now. So I think it's in a GitHub comment. And we tested it and we just swapped it and looked at the waveform and it looked almost the same. It should be, and I tested with both MOSFETs and IGBTs, so it should be pretty same. The only issue I know of is the transformer is now gone EOL. So that will be the problem. There's still stock of them, but eventually that will be, and the transformer is actually a flash charge. So it's designed for a phone flash type thing, so.
Okay, no further questions. Then let's thanks to Colin and all the speakers of the session. Yeah.